So it's this one, right? Sine 4x divided by sine x. So
Yeah.
Sine 4x, so that's in the argument of the sine function, divided by the sine of x. Good. And then equals 4 cosine x, and then cosine 2x. Okay, let's see. So the instructions were just to say to verify the identity or something like that. What does it say?
Yeah, it was just
Prove the identity. Yeah, just prove the identity. Okay. You know, these are really hard because there's no set formula for them. None at all. So I can't tell you, oh, whenever you see this, this is how you do it. You just have to try things. And in trying things, you know, sometimes you try something and it doesn't quite work out. So you try something else. So I have no idea what will work. But I do know that I have a whole bunch of identities that I can try and just play around with them and see what comes out of it. So first of all, I have a multiplication of cosine times a cosine. So I have identities for multiplications, right? A multiplication of a cosine that can turn it into an addition cosine, so like a summation of cosines. So that potentially could be useful. And then I'd end up like adding and subtracting them, I think. Yeah, you add them and then you subtract them. So I'd end up with like cosine 3x on one case, and I'd end up with cosine of x for the other one. So that cosine x sounds good. Cosine 3x sounds like I'm making it more complicated. So I'm not sure if that's the right way to go. On the other hand, I also have the double angle identities for sine. So I think the first thing I'm gonna do is kind of try that and see how that works out. That should give me a 2x, okay, cosine x, so that gives me that, cosine. Okay, so, you know, this is sort of side work. This isn't the actual solution, right? Side work. Okay, on your side work, you're allowed to work on either side at the same time, and you're trying to get to a point where both sides are equal to each other. You can do any kind of transformation, substitution, cancellation. The only thing you don't want to do is anything that goes across the equal signs. You don't want to multiply both sides by anything, right? The wrong thing to do is to say, I'm going to take this and multiply this by sine x, and that cancels with this, and let's multiply this by sine x, right? This is not an equation that we want to solve. We want to show that this identity is true, so we can't go across the equal signs. Is that okay? So we don't want to do that. All right. Okay, so I'm going to start with this thing over here. And I'm going to use this. Sine 2x is equal to 2 sine x cosine x, right? That's one of our identities, a double angle identity. So I'll use that. And so in my case, I have 4x instead. So I have sine 4x. Well, it just means I can rewrite this as sine of 2x. Right, so now this is the x. Okay, so then it'll be 2 sine of 2x cosine of 2x. And peeking over to the other side, I know that there's a 2x, so that's fine. So if I can just get this divided by sine x to be equal to cosine x, then I'll be home free. Good. So I think now if I apply the same property one more time, 2 and then times 2 sine x cosine x, I get that, cosine 2x. Okay, and then I can see that I'm going to be able to divide the sine x here, and then there's a 4, and then that'll look just like that. Good. So for my side work, I'm ready to go. It was actually pretty easy. I got lucky that as I unraveled this thing here, then this side just popped out. Good? Okay, so now I'm ready for my formal presentation proof. Now I'm confident that I know what I'm doing. Proof. I'm going to start on this case on the left-hand side. So left-hand side. And so starting with the left-hand side, we have sine of 4x over sine x. And so that's equal to twice sine 2x cosine 2x all over sine x. Good. And now I can say, well, that, applying that double angle formula one more time, I get 2 times 2 times sine x cosine 2x, and the whole thing is divided by sine x still. Good. Now these sine values cancel, and I'm left with 4 cosine of x times cosine 2x, which is the right-hand side. So I've gone from the left side, manipulated it, and made it equal to the right-hand side. I'm done. I've shown that this sine 4x over sine x is is equal to 4 cosine x cosine 2x is an identity. Good. Any questions?
Great.
No?
Thank you.
Sure, no problem. For tomorrow's test, make sure to get full credit that you do your side work, and I do want to see the side work, right? It's important to see where it comes from. And then you need to put it into a nice formal presentation, right? You have to start on one side, either the left side or the right side, and manipulate it. You can use any of the identities that are in the boxes in chapter 7. There's some in chapter 6 as well, 5 and 6 or 7. Any of the known identities, you could just use them and you don't have to prove them or anything like that. So the double angle formulas, those are just known identities that you can apply. They're available to you without proving it at all. But you do need to organize it this way. Left-hand side equals, right-hand side. Good. I cannot harp enough on this thing. You cannot just multiply both sides of this by something like sine x. Okay. Good. You can't square both sides. You can't take the root of both sides. You can't subtract something from both sides. There's no both sides when we're dealing with an identity, right? That's not how you prove an identity. Okay? Any other questions on this one or anything else from homework? No? Okay. No? We're good? Okay, so everyone's ready for tomorrow's tests. We're all set. Cool. All right then. Well, I will move on then. We left off our last exciting adventures with 8.1, an introduction to the polar coordinate system and comparing it to our standard rectangular coordinate system. It's also called the Cartesian coordinate system, either one. And it's nice to have something different to compare it to, right? A whole new perspective on how to map a grid and identify a coordinate system, to be able to identify a location of a point on that grid, right? They both reference it from an origin, from a central point. Okay, so let's expand that to section 8.2. So let's delete this. And this was this thing. Let's delete this. Okay, 8.2, graphs of polar equations. Okay, so we're looking at graphing polar equations, sketching it by hand, but you'll very quickly see that it's really hard to do this by hand. So we can just get like a nice rough sketch of some of the simpler ones, but we're going to really want to rely on technology to really do the heavy lifting. But at least if we do a few of the simpler ones, we get a real good sense of how it's done. And then even if we can't really do the harder ones, we can at least gain some appreciation for what's happening. And once we see the technology do it, we can kind of confirm that it makes sense, that the image you're getting is consistent with what you think is happening with that equation. Right? So there's some value to doing some of the simpler ones. We're going to be looking at symmetry that exists, and again, that'll help us do a little bit of rough sketching to kind of get a good sense of what the graph should sort of look like. And then again, we're going to use technology to graph them. Okay, so the graph of a polar equation is going to be r equals to f of theta, consists of all the points that have at least one polar representation, r comma theta, whose coordinates satisfy the equation. Right, so many of these curves arise in mathematics and applications. Okay, so this is akin to our rectangular coordinate system, right? So if we defined in rectangular, we have something like y equals f of x, right? That's our function, and in this rectangular setting, we have a x value, which is the input, right? This is the domain values. They go in here, and then we have some sort of an output situation, which is the y, which is the f of x, which is the range, right? This is the range values. This is the outputs, right? So we have this whole conversation of inputs, outputs. So we choose some value in the domain of the function, we input it, and then out will pop out, right? So out will pop out an answer. Like for instance, if x was equal to 2, and then we plugged that into our function, and it squared it, and then added 1, and then divided by something, and then multiplied by something, right? There's all kinds of operations that can be applied to the 2, and out will pop out the output value of that function. I don't know, maybe a 7. Good. So maybe we're multiplying it by 3 and adding 1, for example. Or maybe we're raising this to the power of 3 and subtracting 1, for example. Good. Maybe we're multiplying it by 5 and subtracting 3, for example. Right? I don't know. So here's our input, here's our output, and then we create an ordered pair, 2, 7. Right? Okay. So we keep doing that for lots of different input values. We get lots of ordered pairs. And then eventually those ordered pairs begin to form a shape, an image of some kind. And so the set of all of these is the graph of our function. And often we look for those patterns. Does that graph look like a line? Does that graph look like a parabola? Does that graph look like a circle? Right? Depending on the equation, the nature of the equation will have certain patterns that kind of exist. Okay, so that's rectangular. All right, but now they're pointing out that there's something very similar going on when we want to graph in polar, except that in polar, the input value is theta. In polar, we're also going to create a table of values, and we're going to have theta as our input, and we're going to have r as our output, right? So we pick an angle, and that's going to be our domain. Domain, the input, is an angle, right? So let's say we pick 30 degrees, for example, and then we do something with that 30 degrees. It could be that we take cosine of 30 degrees, and then cosine squared of 30 degrees, plus 2 or something, right? We do something to the 30 degrees, and then we'll be able to get some sort of an r value. It translates into something. Maybe it's equal to 0.2578. I don't know. we took cosine of 30 degrees, squared it, minus 2, divided the whole thing by 9. Who knows, right? There's some sort of a equation that we're going to look at, but at any rate, this leads to that. And so we have an ordered pair that we graph, and that's going to be part of our graph. The only thing that's a little bit different is that in the rectangular coordinate system, we like to write down the x comma y in this order, right? The x comma y, right? The input comma the output. Whereas in the polar coordinate system, that looks like a comma, sorry. In the polar coordinate system, we actually go in the opposite direction. I don't really know why. I don't know, just to make math a little more confusing maybe. Just in case it wasn't enough of a challenge, we decided to throw in another twist. So in polar coordinates, we like to put the ordered pairs in this order. Okay, so this is the theta over here. This is the input. And then this is the output. This is the R value. So we kind of have to read the ordered pairs in reverse. We have to start here. This is the input, and we read it in reverse. This is the input, plug it into our function, out comes the output. Good? Questions, questions, questions? Okay, so we have, whoops. The graph of polar equations equal to R equals to F of theta. So theta is the input variable. And so we have to figure out the domain of theta. It could just be from 0 to 360 degrees. It could be beyond that. Maybe it's all values, all angles. Or maybe it's just a very restricted little domain, right? So you have to be careful about its domain. Also, you have to be careful about whether you're graphing it in degrees or whether you're graphing it in radians, right? By default, it's always radians. I put the 30 degrees here just because I think it's easier to visualize things and to keep in mind that this is an angle. But really, by default, these things are always in radians. So this should really be more like, pi over 4, and then that maps to 0.2, whatever, 993, right? And then the ordered pair would be 0.2993 comma pi over 4 in radians. Good. Questions, 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 questions? No? No? No, 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 no? 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 Okay, so a rectangular grid is helpful for plotting points in rectangular coordinate systems, right? So here's a rectangular grid, Cartesian coordinate system. It's two number lines, right? So here is the x-axis is a number line. Here's the origin, 0, and of course we have positive values in the right, 1, 2, 3, 4, 5, negative values to the left. And then we have another number line that is perpendicular to it, the y-axis, and then positive numbers count up and negative numbers count down. We're very familiar with the rectangular coordinate system. And so if we want to identify this point right there, we use this ordered pair, 4, 2. We go 4 units in this direction, right, the x-axis direction, and then we travel 2 units in the perpendicular direction, in the y-axis direction, and that's how we get to this point. Right? The exact same point on a polar system would be this point here, and it would be identified by this ordered pair in polar coordinates. Where remember, we read these in reverse, we read them this way. We start off with a pi over 4. So pi over 4 indicates that if we create an angle from our polar axes, that's the positive x-axis direction, this thing is the polar axis. If we go from there and we create a 45-degree angle, a pi over 4 angle, right? We create this ray, and then we travel along the ray by 4 units. So that's what these little circles are. They're showing you units traveled along a ray. So that's 1 unit, 2 units, 3 units, 4 units. And that's how we get to that point. Good. On the rectangular coordinate system, we have a 2, 3 over here, right? -2 this way, 3 this way. -2, 3 gets you to this point. Where on the polar coordinate, we get to this point over here by first identifying this angle. This is 5 pi over 3. 5 pi over 3 is 150 degrees. So we go past the 90 degrees, past pi over 4, I'm sorry, pi over 2, and we go all the way into 5 pi over 6, 150 degrees. So we create this ray that goes this way. Let me put it on there. So the first angle creates a ray that travels, in this direction. Sorry, I'm not going to try and make it straight. Yeah. That's what happens when you try too hard to make it straight. Okay, that's not good. Whoa. Go back to the zooming things. Anyway, okay, so if we start, green, start here and we travel, okay, that's my last chance. Go that way. That's supposed to be a straight ray. Anyway, the angle from there to there is 5 pi over 6, and then we travel 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units to get to that point, and that's where this point lands, right? 5 pi over 6 is the angle, and then we travel 6 units along the direction of that ray, and that's how we get to that value. Good. Questions, 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 questions? No? We're good? Good, 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 good. Okay, so that's the comparison between the two. We use such a grid to help us sketch polar graphs. Okay, so let's graph these. Sketch a graph of the equation r equals to 3 and express the equation in rectangular coordinates. Well, this one is a little unfortunate, I think, because it's maybe a hard one to begin with. It kind of doesn't fit the expected pattern, I guess. So this one is a little like graphing the line, y equals to 7 in rectangular. Right? How do you explain this one? Or how do you explain the line x equals to 3? Right? Line, this is a line, definitely a line. Line y equals to 7 or the line x equals to 3. Well, okay, create an ordered pair of the solutions to all of these, x comma y, and this is saying that the independent variable x is free to be anything as long as the output is always 7, right? So the input could be 3 as long as the output is 7. The input could be -2, but the output better be 7. The input could be pi over 9, but the output better be 7, right? That's what this is saying. The output is always 7. Whereas this is saying, well, okay, when you create your table, the input better be a 3. The output is not represented in the equation, so it's free to be anything and everything. So if the input is 3, the output could be 9. The input is 3, the output could be, I don't know, pi squared. 3, that could be 0.25, right? It doesn't matter. The output is not represented there, so by default it means it's all of them. Anything and everything, as long as you're not violating some math rule, but we wouldn't be. So, okay, when we graph all of these, the graph is going to look like a straight line. When we graph in the rectangular coordinate system these two lines, we end up with the line y equals to 7 is a horizontal line, right? If you're allowed to pick any input value, any of them at all, and the output is always 7, then you end up with all these points that have a height of 7, And so this line is considered the line y equals to 7. Good. On the other hand, if the output is allowed to be anything at all, as long as the input could only ever be a 3, then we end up with a vertical line that looks like this, and it gives you the line x equals to 3. Good. So the output is anything at all, and that's supposed to be on the line. Oh, you get the point. That's a straight line. Good. So for example, this could have the point -2, the point 3 comma -2. 3 comma -2 could be on there, or 3 comma 9 could be on there. Good. Whereas over here, this one could be the point -4 comma 7 could be on there, as long as the output is a 7, or 5 comma 7. Right? And where do they cross? They cross at the point 3 comma 7. Good. Okay, so that's rectangular. And then these two are kind of unusual cases, right, in rectangular, when they just equal a single number. And it's such a simple looking statement that it looks really confusing. Like, what do you mean y equals to 7? How am I supposed to graph y equals to 7? So it just takes a little bit of thinking of what that means. Well, we're in the same boat over here, where r equals to 3 means that r has to be a 3. So when we create our table of ordered pairs, remember that the domain value is a theta for polar, and the output is an r. So this is saying the output better be a 3, always a 3. Doesn't matter what the theta value is. The theta value could be any angle. So I don't know, maybe it's pi over 2, or maybe it's pi over 3, or maybe 2 pi over 7, or whatever, right? 2 pi and dot, 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 dot. It could be any and all angles. So no matter what angle you choose, we always get a value of 3. So what would the graph look like if, as we choose any and all possible theta values, it always creates a ray on which we travel exactly 3 units away from the origin? Right, so then think about that. If we have, let's just pick one of them. Here is the polar axes, and then I don't know, we pick pi over 6. So here we have a ray. This is pi over 6, and then we travel 3 units along that direction. 1, 2, 3. So we arrive at this point right there. Good. Okay, and then we pick another angle, and maybe this time the angle is, I don't know, over there. So maybe this time it's pi over 3. And then we travel 3 units along there. 1, 2, 3. So we get to another point. Right? And we keep going, right, for any and all possible angles. Is it clear that at some point there's going to be an angle that kind of comes through here, and then when we travel 3 units along there, the next point is going to be maybe around there somewhere? And then if the angle is just angle 0, then we're going to travel 3 units this way. It's going to be somewhere around there, and we'll get, in the rectangular coordinates, it would be the point 3 comma 0, but in polar coordinates it would be well, same thing actually, 3 comma 0 and 3 comma 0, but in polar. Good. Okay, so if we keep going, is it clear that eventually we would form a circle? Wow, this is ugly, but you get the point. Eventually we would form something that looks like that, right? A circle. Questions, 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 questions? No? 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 We can also confirm that with a little bit of work, because if we take r equals to 3 and we square both sides, r squared equals 3 squared, and then we use our conversion factors for rectangular coordinates. Remember that we have from 8.1 that this is true. So we can replace that in here, and we get that x squared plus y squared must be equal to 9. So yep, this is a circle. Circle in rectangular. Right? We transformed it into x and y, which is rectangular, and we see that there's a circle centered at the origin with radius 3. Centered at 0, 0 with radius 3, right? And that's what we're getting in polar, right? So a circle in polar is just r equals to 3. Good. Any questions? A circle in polar. So a circle in polar looks a lot simpler than a circle in rectangular, right? I think you'll find that in general, graphs of things that are really curvy and complicated, but a lot of curves to them, tend to be a little easier in polar to explain, right? The fact that you're rotating through angles automatically makes those kinds of equations a little bit simpler to express than they are in rectangular for the most part. But rectangular does really well in other things as well. Lines, for example, or any polynomial is really easy in rectangular and not so easy in polar. Pros and cons. Any questions? No? Let's see what the author did here. The graph consists of all points whose r-coordinate is 3, that is, all points that are 3 units away from the origin. Okay, so there's a prettier picture of what I did. It's a nice circle. Notice that for any angle, we create a ray, and then we travel 1, 2, 3 units along that ray. So eventually, we gather all these points and form a circle centered at the origin with radius 3. And we can also use our conversion to convert it back to a rectangular coordinate equation, and we can confirm that this is in fact the circle centered at 0, 0 with radius 3. Any questions? No? Okay, so of course they're going to get a little more complicated. That one was kind of complicated because it's one of those special cases where it was such a simple initial statement, r equals to 3, that maybe it kind of causes a little confusion. Just like in the rectangular coordinate system, when you first look at the special case equations of x equals 7, like how do I graph x equals to 7? So that takes a little bit of work. Okay, but now let's get to a more sort of traditional expression of a polar equation, which has both an input variable theta and an output variable r. Right? So remember, theta is the input, r is the output. So when we write down an equation in polar, we have to solve for r. R equals to something in thetas, so that we can create those ordered pairs and then be able to graph those and eventually see a pattern. Right? That's if we're doing it by hand. That's the most appropriate thing to do. Good. So again, we have some patterns that happen based on the type of equation presented. So polar equations are presented that way. Here's this set of equations that have certain patterns that fit, and then their graphs will end up being a particular type. So in general, as a general guide, if we have something that fits the pattern of r equals to 2a sine theta or r equals to 2a cosine theta, these are circles with radius absolute value a centered at the points with the polar coordinates of a comma pi over 2 or a comma 0 respectively. Good. So these are going to be circles, right, with centered at points with polar coordinates. So pi over 2 is 90 degrees, comma a. So it's going to be on the vertical axes, the y-axis in rectangular, and then you travel a units, whereas this one is on the polar axes, formerly the x-axis in right apart, and they have a radius of absolute value of a. Okay, good. Okay, let's look at an example. Sketch the graph of r equals to 2 plus 2 cosine theta. Hint, sketch the graph of the cosine transform in rectangular. Okay, so let's look at this. We want input-output values, and we can either create a table, which we will do we'll do that in a second. We'll create a table, and then that gives us ordered pairs, and then we want to graph all those ordered pairs. Or in a case like this one, we can also create a sketch of this graph in rectangular coordinate systems using our transformations that we've learned before, and then that will give us a good guide as to what the ordered pairs are in polar, and how to create that sketch in polar. Okay, so let's just do that. So we know that the graph of cosine, sort of a rough sketch of cosine, just looks like this, right? It starts there at +1, comes back down, goes back up, and comes back up like that. This is 1, and this is -1, and this goes out to, let's just do some of the key points. This is going to be 2 pi over there. This is 3 pi over 2 right in there. This is pi over 2, then right there is pi, and then 0. Right? So it experiences this point there at pi. Good. Okay, the fact that we multiply it by 2 out here, that's going to affect the amplitude of it, right? So instead of going out to a maximum value of 1 and down to a minimum value of -1, we multiply everything by 2, so it'll go up to 2. Right, so let's see, this one's cosine of theta. So now let's do cosine 2 theta. Cosine 2 theta is going to be even more dramatic. Oh, that's really ugly. Something like that. But it goes up to +2 down to -2. And we still have all the same values here. This is still pi over 2. Over here, this is still pi. This is still 3 pi over 2. And this guy over here is still 2 pi. Right? So this one's twice cosine of theta. Good. And now +2. The +2 is going to shift this whole thing up by 2 units. So this will go up to a maximum of 4 units. This minimum will go up to 0, and then this will come back up to this will come up as well. So let's sketch that. This is just going to be something that goes from here, comes down to there, and comes up to there. Right? So this guy is going to be 2 plus 2 cosine of theta, where this reaches up to 4, that's 0, so like where the former middle part used to be, that's going to be the line y equals to 2, so this is a 2. Good. And then this right here is the pi over 2, here is pi, this guy over here is 3 pi over 2, and then over here we have 2 pi. Okay, so there's our graph of this. R equals to 2 plus 2 pi cosine of theta. Good. So using this, we can kind of sketch things a little bit. We can also kind of create a few ordered pairs in a table that we can use to then graph, kind of create our, sketch our graph. So I'm going to put it over here. Let's put it over here. So I want to ultimately create theta r values, and here are the theta values. and then the outputs are going to be r values, right? Because that's what this is. So, for example, when theta is equal to 0, the output is going to be 4. When theta is 0, the output is 4. Right? This is theta in radians. When theta is pi over 2, then we get an output of 2. When theta is pi, we get an output of 0. When theta is 3 pi over 2, then we get an output of 2. And when theta is 2 pi, we get an output of 4. Good. Remember that if we put these in ordered pair, they kind of go backwards. So ordered pairs in polar are going to be 4 comma 0 and 2 comma pi over 2 and 0 comma pi and 2 comma 3 pi over 2 and 4 comma 2 pi. So we have at least 1, 2, 3, 4, 5 different points that we can graph into a polar grid. So now if we go over to a polar grid, here is my polar axes. We have 0 comma 4 units. Okay, so we go 1, 2, 3, 4 units. Okay, so here's the first one. Angle 0 leads to 4. Okay, now pi over 2, that's going to be like 90 degrees. Okay, so then when I create a ray that goes from here to like there, this is pi over 2, then that leads me to 2 units in that direction, to travel to 2 units, so that's like 1 unit, 2 units. So now I have another point. I have 2 points so far. And then when I go all the way out to pi units, I want to travel 0. So now if I go all the way out to pi, I create a ray that goes this way. That's pi. But then I want to travel 0 units in that direction, so that leads me to this point, the origin, right? This is the same thing as the origin point. Good. When I go 3 pi over 2, that's going to be way down here. I create a ray down here. So this guy goes from there and goes all the way over there. That's going to be 3 pi over 2. Then I want to travel 2 units in that direction. So 1 unit, 2 units. So that leads me to somewhere over there, 2 units. And finally, when I do 2 pi, if I travel all the way around 1 time, I travel 4 units. That leads me back to this guy. Good. So is it clear how this point there is the point 4 comma 2 pi, which is the same thing as the point 0 comma 4. So that's one important note in polar coordinates. Every single point in a polar coordinate system has an infinite number of ways to express that point, because you can always find more coterminal angles to get you to that point. And you can also get to the exact same point by keeping in mind that if r is negative, you travel in the opposite direction. So we can also have arrived at this point by going pi units and then traveling negative 4 values in this direction. Oh, I put this backwards. Man, I keep doing that. Sorry. It's 4 comma 0, right? Travel 0 degrees and then travel 4 units. Travel 2 pi and then travel 4. And like I said, you can also travel pi degrees. Okay, that would be forcing you to travel this way. But now if we make r negative 4, it still gets you to this point right there. Okay, any questions about what I have so far? Okay, so far so good, but it's just not enough to have a picture, right? 4 points isn't enough to have a picture, so we have to do more points. Now, of course, we can rely on our good old basic, back to our good old basic triangle to give us some of the other results. And we'll be able to expand this a little bit. We have 30 degrees, 60 degrees. So of course this is pi over 6. This is pi over 3. This is 1, root 3, and 2. So if I stick in a pi over 6 into here, cosine of pi over 6 is root 3 over 2. And so I'd end up with root 3 over 2 times 2. Erase this thing. Oh, okay. So then, I'll just put it over here. When r equals to pi over 6, and theta equals to pi over 6, then r equals to 2 plus 2 cosine of pi over 6. Cosine of pi over 6 is root 3 over 2 times 2 plus 2 equals to r. These guys cancel, so you're left with 2 plus root 3. Good. So we can get our calculator and approximate that. Root 3 is like 1.73, I think. Put here. Okay, so I'm just confirming what this is right here. So this is root 3, second, root 3, enter, plus 2, enter. We get 3.732. And that's what goes into here, 732. R equals to 3.732. And so this would be 3.732. Okay, so now again going back to our polar grid, that means that if I create an angle of pi over 6, erase some of this, so hopefully it doesn't get too crazy. I just want to erase that guy. Okay, that's enough. Okay, so if I create a ray that goes maybe like right around there, that's going to be pi over 6. And then if I travel a little less than 4 units, 1, 2, 3, there's 4 units. And so a little less than that would be the 3.7 something. So it'd be kind of like around there somewhere. Is that okay? Questions, 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 questions? So this point right on here would be the point pi over 6, comma, 3.732. Good. Questions, 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 questions. Okay, well, let's try pi over 3. Let's go back over here. All right, so now what if this was pi over 3? What would that be? Okay, that's 60 degrees. Cosine of pi over 3, that's going to be a half. That one's going to be easier. So this would be equal to 2 plus 2 times 1/2. These guys cancel to give you a 1, so the whole thing equals to 3. Good? Okay, so now if I create a ray that has an angle of pi over 3, that's like 60 degrees, that might look like something like, I don't know, over here, something like that. And then we travel 3 units along that ray, 1, 2, 3 units. Then we arrive at a point there. Good. So that point right there is the point 3, comma, pi over 3. Good. Any questions so far? They get tricky, I know. Okay, so we've kind of gone about as far as we can go. I mean, we can try maybe pi over 4 is another classic one that we know how to do. So we can figure that one out. But now let's go back to our graph and make sure that these values kind of match up with what we knew was the rectangular coordinate description of this equation, and see what happens in each section. Notice that from 0 to pi over 2, this is the first quadrant, right? This is Q1 right here. In Q1, this goes there. In Q1, the R value started at a 4, and it's going to go all the way down to 2. Right? So here is Q1. The R value started at a 4, and the R value is getting smaller and smaller and smaller until it reaches 2. And I can see that that's going to happen in a nice, smooth, consistent way, that it gets smaller, the R value gets smaller and smaller for all the angles expressed between 0 and pi over 2. So this right here helps me confirm that this part of my graph will look like this. Good. Okay, now over here, let's use a different color. Yeah, let's make it all pretty colorful. I don't know. It's purple. This guy is Q2, right? From here to here. So the R value in quadrant 2 is going to start off at a value of 2, and as the angle increases from 90 degrees all the way to 180 degrees, from pi over 2 to pi, the R value is going to get smaller and smaller and smaller until it reaches 0. So that helps me see that this thing is going to look like this. Oops, that's got away from me. Ah, come on. Ah. There we go. That looks better. Good. As we progress through the angles, the different rays, going from pi over 2 to all the way out to pi, right? From 90 degrees, 110 degrees, 120 degrees, 160 degrees, all the way out to 180 degrees. The distance you travel along those rays is going to get smaller and smaller and smaller until you get to this point where you've traveled pi radians to get to this ray over here, but then you've traveled 0 units on that ray. So you get to the origin, right? That's quadrant 2. In quadrant 3, the R value starts off at 0, but then it gets a little bit bigger and bigger and bigger and bigger until it reaches 2. So this thing is going to look like that. Good. And in quadrant 3, we start off with an R value of 2, and it gradually gets bigger and bigger and bigger until it reaches all the way out to an R value of 4. So we get to something that looks like that. Right? It looks like a heart on its side. Good. Any questions? Any questions? Any questions? Any questions? No? No? Okay, let's look at some of the work the author did. Probably looks very similar, only better pictures. Okay, so first we sketch the graph of r equals to 2 plus 2 cosine theta into the rectangular coordinate. Using transformations, we know that it looks like this, where this is a maximum of 4 there, down to 0, up to positive 4. Good, so hopefully we have that part. This helps us get a few of the key ordered pairs, like that when the theta angle is pi, the R value is 0. When the theta angle is 3 pi over 2, the R value is 2. Okay, so we can get some of those key values, but more importantly, it helps us gauge what the graph is going to do in different zones. Good. So in quadrant 1, theta ranged between 0 and pi over 2, and we can see that the R distance started at 4, 1, 2, 3, 4 units, and it slowly gets smaller and smaller and smaller until we get to pi over 2. Good, 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 good. Okay, in quadrant 2, the angles range from pi over 2 over to pi, and we can see from here that they go from 2 down to 0. So you'll get this little part right here, from 2 down to 0. Same thing happened in quadrant 3. It ranged from 0 up through 2, and then from 2 all the way out to back out to 4. So ultimately, it looks a little like this. Similar to mine, only a little bit better. Any questions at all? So these kinds of equations in general are called cardioids, obviously. They look kind of like hearts. It's got that cardi kind of name in there. Right? So any kind of equation that fits these forms, either an a constant, times 1 plus or minus cosine, or a times 1 plus or minus sine of theta, either one of these general forms will form some sort of a cardioid. Okay, let's try technology with this. What do I want to do? Let's go to Desmos. Well, here's a cardioid right now. So anything that fits that. So what did we have? We had 2 plus, equals 2 plus 2 cosine of theta. So Desmos is actually not that great with polar. I love it for anything rectangular. It's actually not that great with polar. If you're wondering what in the world this whole thing is over here, well, it was a way to create the grid. See that grid underneath here? So that's what this thing is doing. So if I like turn off r equals to 1, it turns off that inner circle. And then if I turn off r equals to 2, it turns off that second circle, that concentric circle. So this is, all of these equations over here are part of what makes the grid. All these tangent things, all of these things are part of these. Watch, if I turn off one of these things, one of those lines disappears. Okay, so not so great. We kind of have to jerry-rig it to give us the grid and be able to graph it on there. So not my favorite, but we'll do what we can. Okay, so let's see if we can add a... Let me see if it'll work if I add a table with these values. Nope, it doesn't like it. Okay, so let's see. If I put in a 0 in there, we get a 4. Okay. And if we put in a pi divided, well, pi gives you the 0, good. And a pi divided by 2 gets you to 2. Okay. So as you can see, it's not going to match up perfectly well. Why doesn't it match up? 0, 4. Yeah. At any rate, I don't want to do this then. Okay, what we could do though is play with this thing. 2 pi. Okay, so if this just went from 0 to pi over 2, pi divided by 2. Okay, so we can at least get that this is the part that gets graphed when theta ranges from 0 to pi over 2. And we can get that this pi divided by 2 over to pi is the part that gets grafted by pi to pi over 2. From pi over 2 to pi. Okay, well, I mean, it's pretty much giving you the same thing as before, huh? Nothing pretty. I also pulled up a GeoGebra graphing tool. See what this looks like here. So let's type in 2 cosine 2 plus 2 cosine of t Okay, so here's 1 period of the cosine function. And, oh, good. Okay, this is a nice little grid. That's kind of cool. Make it a little bit bigger. Okay, so here is the cosine, the 2 plus 2 cosine function. Right, the input variable here is t instead of theta. But okay, so then as we go through here, so here is what the graph looks like. Oh, can I zoom out a little bit? There we go. So here's what the graph looks like as the angle ranges from 0 to pi over 2. Then it begins to graph this thing. Can I use this as a slider? Oh, perfect. From 0 to pi over 2, it graphs that. From pi over 2 down to pi, it graphs that. And then from pi to 3 pi over 2, it graphs that. Yeah, I like this one much better than the Desmos one. Good. Does it make sense? Any questions? Any questions? Notice that then it begins to repeat itself, right? Because then it'll do another another period of this function, and then we'll just begin to retrace our cardioid. So part of these equations, part of the difficulty is going to be figuring out when to stop, when you've completed one whole image and you begin to retrace your image. Good, good, good. Okay, so what would happen if we have a different constant in here other than a 2? What if this was a 3? 3 there. Put a 3 there. Oops. Wait, what happened? Didn't like it. 3 there. Okay, it doesn't like it. Why don't you like it? 3 plus 3. Okay, well now I don't know why it's not letting me change the constant there. Maybe I have to hit refresh. Let me erase it out. 3, I'll try 4. 4 plus 4 cosine of t. Okay, well then that took it. So what happens if we multiply by a 4 plus 4? Okay, so then that just changes this, and it gives us the exact same shape. It's just that it gets a little bit bigger, right? That's what happens if we change those constants. What if we change it to a minus? Minus. You know, like that? Okay. So look what happens if we change it into a minus. If we change this into a minus, how does the cosine function get changed? We multiply by -4. It's going to be a reflection about the y-axis. It's going to flip it upside down and then shift the whole thing up. Right? So before we used to have cosine come down here this way and do that, but now it got reflected about the x-axis, and that's why it's kind of an upside down cosine. Now how does that affect our image? Right? In the first quadrant, we start off at 0 and grow up to 4. Right? That's what we get there, starting off at our value of 0, growing up to 4. And then in quadrant 2, we start off at a 4 and grow even bigger into an 8. Oops, into an 8. Then we go from 8 back down to 4. And then from 4, we go back down to 0. Good, so it still made a cardioid, it just changed it in the other direction. That's what happens when we change it from a plus to a minus in here. Good, 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 good. Okay, and then what happens if we change this equation into a sine instead of a cosine? Nope, I didn't like that. How about 2 plus 2 sine of t? Okay. So then in quadrant 1, we're going to start off at a 2 and go up to a 4. So our value of 2 reaching up to a 4. That's quadrant 1. And then in quadrant 2, we're going to start off at a 4 and go back down to a 2. Good. In quadrant 3, we're going to start off at a 2 and go all the way down to a 0. And then in quadrant 4, we're going to start off at a 0 and head up to a 2. So we finish off that cardioid. Right? So the sine one looks like this. And I think that if we change it from a plus to a minus, it's going to be a cardioid that's kind of facing the way we think hearts should face. Like that. Good? Questions, 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 questions? So in quadrant 1 it does that. Quadrant 2, quadrant 3, quadrant 4. Good. So next Valentine, you don't have to give your special someone a heart. Give them a 2 minus 2 sine theta. That would look great on a cake. No? All right. You can engrave your wedding ring with something like that. A little math equation on there. Nothing says love more than 2 minus 2 sine theta. No? No one? No one? All right. Any questions on this? Right, so cardioids, they fit these patterns. And of course, things can get more complicated, right? What if we squared them? What if we multiplied sine times cosine? What if, right? So all those things are just going to have different patterns. Some of them are recognizable patterns, but some of them are just kind of weird little equations that can get very complicated. So in cases like that, just create a table and use technology to graph them. Okay, this would probably be a good time to introduce our calculators to do this, since we don't always have Desmos or GeoGebra on hand to do this. So let's do the this equation, or whatever, this guy. So go to your calculator, TI-84, and then you're going to go over to where it says mode, and you're going to go down to where it says functions right here, and we want polar, right? We want to graph in polar. So go down, 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 to the right, polar, hit enter. Okay, and that's it. Now, for the angles themselves, like I said, by default, we really like to work with radians here. So make sure that you're in radian mode instead of degree mode, right? The graphs look better. Otherwise, the input-output ratios are just crazy, right? Because if the inputs are angles and they range from 0 to 360 degrees, and the outputs are these little equations, like here, we have a cosine bounded. This thing was bounded between 0 and 4, and then you have the other input variable is from 0 to 360. It's just not going to look right. So the graphs just look better in radians when we graph polar. Okay? All right, so radian and polar. Now go over to where it says y equals. And now notice that before it used to have y sub 1, y sub 2, y sub 3. But now, because your calculator is in polar form, it has r's in here. It already knows that. Okay, so let's type in 2 plus 2 cosine of, and then before when you push this button you would get an x. Here you will automatically get a theta. Again, your calculator already knows that you're in polar form. Good? Good, good, good. Okay, next you're going to go over to your window, and now we got some special settings to go through. You're going to identify the domain of the theta value. Remember, you're in radians, so 6.2831, this is 2 pi. Good. just for the sake, we'll come back and change this, but for now, let's just do the first quadrant. Let's just graph quadrant 1 from 0 to pi over 2. So this would be pi divided by 2. Enter. Good. Now, theta steps means how many individual little dots you want to go by. So, for example, if I just put this as 1, this would be terrible because it's just going to go from 0, 1, and then 2 is too big, so it's only going to give me like 2 dots, right? So that's not going to work out. So you want more dots. On the other hand, if I go by 0.1, now what this is going to do is it's going to graph a point when theta is 0.1, graph a point when theta is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and then go all the way from 0 all the way out to 1.5. But, okay, so that's a little bit better. If I want even more detail, I can put that, and then that would go through even more individual little dots. So the drawback of making it too detailed is that, you know, it takes the calculator a really long time to calculate all those individual little points, so it will take you longer, and you might run out of, you know, RAM depending on your calculator, and so you don't want to make it too detailed for this. Okay, so let's see what happens there at 0.01. And then you want to be able to create a window for your actual image. So remember that the R value is bounded by 0 to 4. So say -5 to 5 seems like a pretty good window to just kind of gauge what will happen. So let's just try doing that, and we can always come back and readjust it later. Okay, so we've chosen some of those things, and let's go graph it and see what it looks like. There it goes. So there's quadrant 1. Goes there. Good. If I wanted to do just quadrant 2 by itself starts off at pi divided by 2 and goes over to pi. Graph, that's just going to be quadrant 2. Good. Okay, enough messing around. Let's do the whole thing. We have from 0 to 2 pi. 2 times pi. Enter. Graph. Good. Questions? No? We're good? Good. Okay, then let's keep going over here. We can think of this as a graphic table of values that enables us to read and glance the R values corresponding. Okay, so it's everything I've been talking about. Okay, so we did that, we talked about that, we looked at the cardioids in general. Okay, so now let's look at this one. R equals to cosine of 2 theta. And again, hint, first sketch the graph in rectangular coordinates. What happens to the graph of cosine when we multiply the argument by a 2? Right? It makes the period go twice as fast, right? We experience all the results of cosine are experienced in half the domain of theta. So here is a standard cosine function. Would go from here and come back down and go back up and go like that. So here's the standard one in 2 pi from 0 to 360. It's cosine of theta. But now cosine of 2 theta is going to go twice as fast. It's going to experience all the same values. It's just going to do it in half the time. I don't know. Something like that. Good. So this guy is pi. Good. Okay, well then that means that it can do 2 cosine functions in the same space. Oh, that's supposed to be there. Anyway. So you can complete 2 cosine functions in the same space that you would normally only do 1 cosine function. Good. Okay, so now that we have this, then we can get a rough sense of what's going to happen to our image when we graph this based on the quadrants. So in quadrant, well, you can also find the zeros of this thing and figure out where all these zeros are and figure out when the R value is going to be equal to 0. But these quadrants stay the same as this guy. So here, this is going to be pi over 2. So from 0 to pi over 2, this cosine value is going to go from a value of 1, right, all the way down to 0, and then all the way down to a value of negative 1. Good. And then from pi over 2 to pi, it's going to start off at negative 1 and then come back up to 0 and then go all the way back up to 1 in quadrant 2. Good, good, good. Okay, let's see. This is a much better picture. So here we have the cosine function, kind of elongated a little bit. Right, so 2 periods of cosine fit in the same space. Right? Normally we would just have 1 cosine function in this whole thing, but here we have 2 of them. And so we can figure out where all these are by symmetry, right? Because if we divide this cosine function into 4 equal parts, then this part is obviously pi over 2, and this pi is half of that is pi over 4. Right? And then so this must be 3 pi over 4. We can also turn it into decimals. It might make more sense that way. Since it's 4 equal parts, this is 1/4 of a pi, half a pi, 3/4 of a pi, or 0.75 pi. This is 1 1/4 pi, 1.25, 1.5 pi, 1.75 pi, and then 2 pi. Good. Okay, so then we can break it up into little regions. And we can see that as the angle ranges from 0 to pi over 4, it's going to go from an R value of 1 down to 0. And then as it ranges from pi over 2 over to, pi over 4 to pi over 2, it's going to go from 0 all the way out to negative 1. Do an ugly hand sketch of that, and then we'll see what technology can do for us. Any questions about this whole thing here at all? Right, so quadrant 1 is going to figure out what happens with these angles that are between 0 all the way out to pi over 4. Right, all of these rays that are created here. Here are all the rays that go from 0 to pi over 4. And then my R value starts off at 1 unit apart. So here's 1 unit. Here's my first one. And then they slowly get smaller and smaller and smaller until at pi over 4 they go back to 0. Right? So they get smaller. The next one's going to be a little smaller, then a little smaller, and then a little smaller. So I end up with something that looks like this in that first little space, right? This is that first little value right there. Good. And then from pi, I know, let's put it in color. So this is the 1, and then for 2, from pi over 4 all the way out to pi over 2, that would be all of these rays that exist over here, all of these rays that are created by angles between pi over 4 and pi over 2. All of those guys go all the way out until you get to pi over 2. They start off with a ray value of 0, and then they get slowly bigger and bigger and bigger and bigger and bigger and bigger until you reach a negative 1. So they bigger in the negative direction. Sorry, that sounds confusing. So at pi over 4 we have 0. Slightly past that we have a very small negative number. So remember that when an R value is negative, you travel in its opposite direction. So this is going to start off at 0 and slowly get bigger and bigger and bigger and bigger until you reach pi over 2, and then it reaches negative 1, which is going to be like over here. So this is going to be something, oh, it's looking green, something that kind of goes like that. Does that make sense? This is 2. So even though the angles are in quadrant 1, right, it's the angles that are between 45 degrees and 90 degrees. Those are all those angles. But the R values are negative, so you're going to travel in its opposite direction, and you're going to trace out this little part over here. Good. Questions, 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 questions? For the next part, 3, okay, now you're in quadrant 2, and you're tracing out angles between pi over 2 all the way out to 3 pi over 4. So that's going to be angles that are like around here, around there, around there. Right? So here are all the rays that are created by those guys. But again, you have negative R values. So when we start off with pi over 2 and negative 1, we end up with a dot way over here. And then as we travel into quadrant, in quadrant 2, this thing is going to end up giving you things that look like that. Good. So this is part 3. Let's do one last one. Part 4, we start off, we're still in quadrant 2. We're going from pi over 3 to 4. So we're going to create all the rays, or think about all the rays that extend into there to give you all of these things. However, the R value starts off at 0, and it gets bigger and bigger until you get to pi, and you end up with something that looks like that. Wow, that's really ugly. Something that looks like that. Good. Sort of, kind of, maybe. I know this is really messy. We'll use technology now, and it'll hopefully look a little better. Let's try that GeoGebra one. This thing did a really good job. And let's bring this down over here. And was it just cosine 2 theta? 2t? Okay, so here is that cosine function. Notice that 2 periods of cosine fit between 0 and 2 pi. And then now, as we begin to trace this guy from 0 to pi over 4, we trace out that little guy. You know what? Let me zoom into here. Okay, so from 0 to pi over 4, we trace out that part. And this is where it gets really, really tricky, because the angles are still in quadrant 1. We're ranging from pi over 4 to pi over 2, and then we trace out that part. Got it? This is the result of rays that are over here in quadrant 1, but the R value is negative, so you're actually traveling into quadrant 3. Then we start off in quadrant 2. Angles that are over here, the rays are over here in quadrant 2. They're ranging from pi over 2 all the way to 3 pi over 2. And the R value is negative, so it traces out that. Oops. Traces out that. And now if we keep going, stop it. If we keep going, then the ray values are going to travel from they're traveling from 3 pi over 4, what did we say? I forgot. Yeah, 3 pi over 4. From 3 pi over 4 to pi is the next little segment. From 3 pi over 4 all the way out to pi, which are still in quadrant 2, but the R values are now positive, and they range from 0 all the way out to 1. So this is what I tried to do by hand. And that covers one whole period of cosine. Good. And now as we keep going to cover the next period of cosine, we see that it will do this. Good. So it ends up being like a little flower. Any questions? Any questions? Any questions? No? No, no, no. Okay, what happens if I change it from a 2 over to a 4? Well, then we end up oscillating cosine faster, right? We go through its period faster. So what's going to happen is that as I trace this in polar coordinates, it completes those little petal things faster, and so we end up fitting more and more of those petals in the same space between 0 to pi over 2. So look, we have another little flower with more petals. The bigger this constant is, the more petals we have. Good, let's try a different one. What if this was, let's get really crazy here, how about 10? So there's cosine, and then as we trace this, it just gives you that. So there it is from 0 to 2 pi. Right? So you can have a heart and you can have a flower. 2 minus 2 sine theta and cosine 10 theta, say love. I need coffee. It was a dumb joke. Anyway, any questions? No? No? So we've established the pattern for things that fit the form cosine 2 theta. Right, so that's what this is just indicating for us. So we have a 4-leaf rose. So these are just roses, and then anything that fits either of these two patterns will be an n-leaf rose. Either a cosine n theta or a sine n theta will be the rose, and then the A will just make it bigger or smaller, right? So how far it extends from the origin. Good. Any questions? Any questions? Any questions? No? No, no, no? Okay, to help us in doing these rough sketches, symmetry would be nice. So we establish 3 different kinds of symmetry with polar equations. So we have symmetry about the polar axes. That's this, that if we have angle theta and angle negative theta, we get the same R value. Right? So we have a symmetry about the polar axis that looks like this. Symmetry about the pole is a case where the same angle theta can result in R and then also negative R. So we have both this point at this point for any angle theta, then you have symmetry about the pole. And then symmetry about the line theta equals to pi over 2, our old y-axis, is something that fits this form, where whether you type in theta or whether you type in pi minus theta for any value of theta, that you always get the same R value. Good. So if you type in degrees 30 degrees and 150 degrees, you get the same R value. Good. Or pi over 6 and 5 pi over 6 both give you the same R value. Then you'll end up with a symmetry about the line pi equals pi over 2. You know, these things were a lot more useful when we had to do all equations by hand. Nowadays, I think that if it's a simple, straightforward one, then you can kind of do it by hand. I don't think you really rely too much on these symmetry things. If they get overly complicated, then I think you're just kind of expected to go use your technology. So I wouldn't really say that we use these too much when we're trying to sketch something. But it is useful for the purposes of homework in this section, because sometimes they ask you to establish if a polar equation is symmetric. And so this is what you fall back on. All right, so to establish that, to establish symmetry, testing for symmetry, here is the little guideline, right? If a polar equation is unchanged when we replace theta by negative theta, then it's symmetric about the polar axis. If the equation is unchanged when we replace r by negative r, or theta by theta plus pi, then the graph is symmetric about the pole. And if the equation is unchanged when we replace theta by pi minus theta, then the graph is symmetric about the vertical line pi over 2. Okay, so the questions that ask you test for symmetry, this is your little guideline on how to do it. Here's some nice little graphs that we've worked with. So we had r equals to 3, we had r equals to 2 plus 2 cosine theta, we had r equals to cosine of 2 theta. And here's another one. I'm not sure what that one is. Just like a circle of some kind. Anyway, we can establish symmetry. The graphs in figures 2, 6, E, and 8 are symmetric about the polar axes. The graph 8 is also symmetric about the pole. Graphs 4 and 8 are graphs that are symmetric about pi over 2. Okay, so it just takes playing around with these a little bit and kind of visualizing. But like I said, the symmetry thing is really more about just answering the questions that ask about symmetry. Things like this. Sketch a graph of the equation. So they might ask you to find the symmetry first. We use the following as an aid in sketching the graph. Symmetry, since the equation is unchanged when theta is replaced by negative theta, the graph is symmetric about the pole. How do they know that that's true? Well, just remember, it's as simple as knowing that, if we have our sketch of a cosine function, looks like that, right? And it extends this way, of course. So that means that if I put an angle in here that leads to there, then negative a is going to lead to the same thing, right? We said that cosine is even. Cosine of theta, here's theta, is even. Even, right? So that means that cosine of theta is equal to cosine of negative theta. Right? Whether you type in the angle or negative that angle, either way, you get the same output. So this work is kind of easy and a little silly, really. We have r equals to 1 plus 2 cosine of, and then we decide to input a negative theta. Well, then by this property, we know that we can just get rid of that and say that this is equivalent to 1 plus 2 cosine of theta. And so we've established that it's symmetric about the polar axis. We replaced theta with negative theta, and nothing happened. Right? We got the original equation back. It's unchanged by that. Right? For similar reasons, remember that sine of negative theta is equal to negative 1 times sine of theta. Right? This one was odd. So if this original equation had a sign in there, we wouldn't be able to do this. Right? It would be noticeably different. Any questions about that? No? We can also find the zeros by setting our equation equal to 0, and that'll help us find the 2 zeros of our graph. And from all that, then we can begin to get a rough sketch of what happens with these, right? With this polar equation. Starting from 0 all the way to 2 pi over 3. We see that the r value starts off at a 3 and goes all the way down to 0. Good. And then from 3 pi over 3 over to pi, 2 pi over 3 all the way over to pi, starts off at a 0 and goes in the negative direction, small negatives down to negative 1. So even though you're graphing in quadrant 2, your angle is in quadrant 2, then that means that your output values, your graph is going to be really graphing in quadrant 4. Good. Does that make sense? And then in quadrant, once you begin your sketching in quadrant 3, you're really going to be doing some graphing in quadrant 1 because the r value is negative up to this point, 4 pi over 3. And then from 4 pi over 3 all the way out to 2 pi, you're going to be in the positives. Does that make sense? Good, maybe, sort of, kind of. So here is what the graph looks like. It's got that little hole in there. And let's put them in by regions. So from here to here in green, this part right there is equal to this part. We start off at angle 0 and we go all the way out to here. So we're at angle 2 pi over 3. Good. And then for, let's pick a different color. See what does yellow look like. For this part over here, this part, it is going to be this part. We're in quadrant 3, but really we're going to be graphing this part of my graph. Good. And then the next part is going to be, I don't know, about, well, let's leave it as blue. Let's leave it as blue. The next part is going to be this in here, which is this part here up to that point, and that point was 4 pi over 3. Good. And then the last part, we'll leave it in black, is this part, and that part ends up being this part. Good. Questions, questions, questions? No. 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 Again, technology is better. Let's try putting it into the GeoGebra one more time. And this was what? 1 plus 2 cosine t. Okay, so here is my 1 plus 2 cosine t. The 2 is going to extend the amplitude up to 2, and then the plus 1 is going to shift the whole thing up. So it used to be that it ranged from -2 to +2 by just this part, but then the plus 2 shifts everything up, so this goes down to -1, goes up to 3. Good. In quadrant 1, I'm doing this thing, and I go past quadrant 1, so quadrant 1, oops, let's zoom out of here. So here's quadrant 1. Quadrant 1, I'm going from there all the way out to there. And then still in quadrant 2, starting in quadrant 2, I go there, and it goes back down to 0. So right there at, what was this? This was 2 pi over 3. We go there. And then we're still in quadrant 1. We're creating rays in quadrant 2. But because now the r value is going to be negative, we begin to draw in quadrant 4. So this little part here is the rest of quadrant 2. That part there is quadrant 2. Good. Now I'm in quadrant 3, and in quadrant 3 I begin life there. This is quadrant 3. The rays are over here, right? They're in quadrant 3, and they go all the way out to, was that 4 pi over 2, I think it was? No, not 4 pi over 2. What did we say it was? 4 pi over 3. So all the way up to 4 pi over 3, I create this little part. From pi to 4 pi over 3, I create that part. So even though the ray is in angle in quadrant 3, I'm really graphing back in quadrant 1 because the r values are negative. And then the rest of quadrant 3 goes from there to there. And now I begin to draw in quadrant 3 because the R values are positive, so I just get that little guy. And then for quadrant 4, I extend all the way out there, and I'm graphing in quadrant 4 because the R values are positive, and I go all the way up to 3. So I end up graphing that. Good. Any questions? Questions? No? No? Okay. So the curve in figure 11 is called a lamacon. I've never really learned how to pronounce that exactly. Lamacon? After the Middle French word for snail. So in general, the graph of an equation of this form, r equals to a plus or minus b cosine theta, or a plus or minus b sine of theta, will have the shape of a lamacon. Okay, so some constant plus or minus b, some cosine of theta will give you the same shapes, just moved around a little bit. So let's play around with those a little bit. So what would happen if this was a, let's change this to this. So let's play around with some of these constants. What if this was a 3 and this was something like that? Come on. About 3 plus sine t. Okay, so here's 3 plus sine t. And as I draw this, we end up with a kind of a wobbly kind of circle thing. Okay, so now if I stick in a constant in here like a 2, it makes it a little bit more of a pronounced wobbly thing here, right? This thing here is not quite a perfect circle. Okay, so let's extend that even more. How about a 4? So now we begin to form a little belly button there when there's a 4 there. And okay, let's change that to a 6. It gets even bigger. Okay, so we start to see some patterns. Make this one smaller. How about this one as a 2? So the inner circle gets bigger apparently as it has something to do with the relationship between these two constants. Right? If I make this one bigger than this constant, let's make this about a 6 there, and okay, about a 6 plus 2 sine t. Okay, so when we have the sine function, the inner circle is formed when the constant here is bigger than the constant there. If this was a plus b sine, we need b to be larger than a to get that little inner circle. Otherwise, we just get kind of almost like a circle, but it's a little bit more wobbly. It's a little more flat, not quite a circle. Good. Okay, so let's go back to the other one. How about if we had 3, about a 2 plus 4 sine t. Back to this guy. Okay, and then what happens if I make this a minus? It just flips it upside down. Okay, let's play around with this thing again. So in quadrant 1, from here to here is quadrant 1, and the R value is going to go down to 0 at some point there, and then go down to -2. So in quadrant 1, I go to 0, and then I go into the negatives, which means I'm really going to be graphing in quadrant 3. Okay. The rest of it goes there. And then the beginning of quadrant 2, the R value is negative, so I'm going to really be graphing in quadrant 4, part of it, until I get to there. And then the rest of quadrant 2, the R values are positive now, so now if I go up to there, I graph some of it in quadrant 2. And then in quadrant 3, the R values are all positive, so I will be graphing in quadrant 3. The rays are in quadrant 3, the points are going to be in quadrant 3, up to a maximum of 6. And then in quadrant 4, it's going to be the same thing, and so we end up with that. Good. Any questions? Any questions? Any questions? No? 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 And so if we put cosine, it's going to be the same kind of image, but on its side, right? Let's see if this will let me. Cosine of t ends up being on its side. Good. And if I put a plus here, it's probably just going to reverse it over to the other side. Plus. Flips it over to the other side. Good. Any questions? Any questions at all? Questions, 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 questions? Almost done. Okay, so these all establish like a little family of shapes in polar coordinates that just kind of happen to fit this pattern. And we've already been doing this. So we can do really cool things like this one. And it's just a matter of typing it into your calculator and watching the fun happen. So that should be no big deal. Or something like this. The only thing that's kind of tricky is figuring out the range in your the domain, the section of the domain that's needed in order for you to trace the full image without retracing it, right? Without going over it again. So you don't want to go too small in the theta section, the domain section of the domain, because then you might not get the full picture. But then if you also make it too big, then you're going to start retracing the graph. Yeah. So go back to y equals, let's get rid of the old one, and let's put in cosine of 2 theta divided by 3, close parentheses, enter. Okay, so this is going to be, the R values are going to be bounded by cosine, right? The fact that we have 2/3 theta in here is just going to make the cosine function oscillate at a different rate, right? If it's bigger than 1, then it oscillates faster. If it's smaller than 1, it oscillates slower. And 2/3 is smaller than 1. So it's going to take it more than 2 pi to complete one period of cosine, one standard period of cosine. Good. All right, let's go to our window and just play around with it. If we just go from 0 to 2 pi, let's just see what happens there. And let's change this from -2 to +2. And then change this from -2 to +2. Enter, and let's just graph it. And we get that, and we get that, and then we get that, okay? And then it stops. So the question is, did it just stop and that's it? That's the whole thing? Or maybe there's more stuff that's happening and we just haven't completed the whole thing yet, right? So if we go back to our window, right, what if I make this just pi, right? Obviously, I'm going to get an even smaller portion of this, right? It just kind of stopped. So I need to go bigger. So you can just kind of guess and check a few things until you get to it. How about if it was 3 times pi? From 0 to 3 pi. Maybe that'll do the whole picture. Okay, that looks better. Maybe from 0 to 4 pi? 4 times pi? Graph? Okay, so you can just kind of guess and check, but it would be better if we had some sort of way of knowing, right? Because guessing and checking can only get you so far. So how do you know when you've completely retraced your graph? Your graph will begin to retrace itself when we can find something that fits this situation. It's got to be a multiple of 2 pi. We have to find n such that adding a multiple of 2 pi into your equation gives you the same output, right? So find the value n such that theta plus that multiple of 2 pi's is equal, it makes this whole statement equal to each other. Right? That's what we want to do. Good, 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 good. If we distribute this, we end up with 2 pi, we end up with 4 pi n. Right? So what we want to do is figure out the multiple of n such that 4 n pi over 3 is a multiple of 2 pi. Does that make sense? Looking at this equation, we divide, remember this whole thing is in, this 3 is inside here. The 3 is part of that, like that. So if we distribute, we end up with 2 pi over 3. And then in here, we end up with 4 pi over 3. So we need to figure out something so that this is a multiple of 2 pi. And then if we have that, then obviously then these two will be equal to each other. So when will 4n pi over 3 be a multiple of 2 pi? When n gives you a value in the numerator divisible by 3 that's a multiple of 2 pi, the first time that happens is when we get a 12 in the numerator. 12 divided by 3, because it's going to be multiples of 4. 4 divided by 3 is not a multiple of 2 pi. 8 divided by 3 is not a multiple of 2 pi. Let me write some of those down. That might look confusing. Yeah, when n equals to 1, we end up with 4 pi divided by 3, not a multiple of 2 pi. When n equals to 2, we end up with 8 pi over 3, not a multiple of 2 pi. When n equals to 3, we end up with 12 pi over 3, which equals to 4 pi, and that is a multiple of 2 pi. Multiple of 2 pi. Good. Therefore, we can obtain the entire graph if we choose values of theta between 0 and 6 pi. Right? This is 0 plus 2 times 3 pi. And this is the whole graph we're going to get. So we were pretty close. We are guessing and checking. Go back to our window, and we need to go from 0 to 6 times pi. Graph, and now we'll get the same thing. There's no way that you would ever be asked to do this by hand. So like you can see, these graphs get really, really complicated. And there it is. Any questions? Your book also gives you a nice little table of standard polar equations, some basic polar graphs. Right, so when r equals a constant, we're going to get a circle. When r equals a constant times sine of theta, we're going to get a circle like this, centered on what we used to consider the y-axis. Now this is pi over 2, the rate pi over 2. And then when we have a constant a cosine of theta, we're going to get a circle centered somewhere on what we used to consider the x-axis. Good. R equals to a theta is just going to be a spiral. We should have done one of those. Those look cool. Lamicons are equations of the form a plus or minus b sine theta, a plus or minus b cosine theta. So the orientation depends on the trigonometric function, sine cosine, and the sign of the b, right? Plus or minus. So we end up with getting things that look like this. And then we have cardioids. They vary from cardioids to these other variation things. Lamicons have that inner loop thing. Okay, and then we had roses, so an n-leaf rose, or 2 n-leaf rows, right? So different equations, but they fit the form r equals to a sine 2n sine n theta, or r equals to a cosine n theta. And then we just get different kind of roses depending on the rose petals. Depends on the constant value n. Good. And finally we get, again, I don't know how to pronounce this, lemniscates. There are figure 8 shaped curves, kind of little infinity symbols. So r squared equals to a squared times cosine 2 theta. Good. Okay, so these are just some of the standard ones, or you can use technology and get a good variety of things, like this one. But that's about all we need to do with polar equations. So last chance for any questions on polar. We're all pretty good with it? Doing okay? Okay, then moving on. So the last section in chapter 8, we're going to skip 8.3. Get rid of this thing, delete that. We're skipping 8.3, and we're going to just do 8.4, and that's the last section in chapter 8 that we're going to cover. And it's on parametric equations. Come on. Parametric equations. So an introduction, a basic introduction to parametric equations, just like we did a basic introduction to polar equations. These are parametric ones. Okay, so we're going to look at plane curves and parametric equations. We're going to work on eliminating the parameter, finding parametric equations for a curve, and then using graphing devices to graph some of these guys. Just like before, the easy ones we do by hand, and then they very quickly get complicated, so then we want to use technology to help us graph them, but we want to get a good idea of what's happening. Even if technology takes over, we have a sense of what the technology is doing. Okay, so parametric equations. We can think of a curve as a path of a point moving in the plane. The xy coordinate of that point are then functions of time. So this idea leads to the following definition. So if f and g are functions defined on the interval I, then the set of points f of t and g of t is a plane curve with these equations. Right? What in the world does all that mean? What this means is that we're going to be looking at situations where the ordered pairs that we're graphing are themselves the outputs of different equations. Measured by a third constant, which is usually t, and we often refer to it or let it be equal to time. So we'll have, for example, let's do a really quick one. There's I guess there's a nice example there. Okay, yeah, let's just jump to this example. So what we have here is a case where we have ordered pairs that we're going to graph, and the input variable is the x usually, right? And the output is the y. But now, instead of letting x just be any value that you can choose, the independent variable within a certain domain, the x coordinate is itself going to be the result of an equation, where the equation is an equation written in the variable t. And the y is also an equation written in the variable t. Good. So the t is called the parameter of these guys. So in order to graph this, we're going to have to create, if we're going to do it by hand, we're going to have to create a table of values. So let's begin with creating a table where we have t values, and then we have our x, which is equal to t squared minus 3t values. And then over here, we'll have our y values, which is t minus 1. So for example, when t is equal to, let's put it right over here, 0, let's get rid of the 7, then we end up with x equals to something squared minus 3 times something. and y is going to be equal to something minus 1, and that something is a 0, 0, and a 0, we end up with x equals 0. That's going to be 0 squared minus 0. So this is just going to give you a 0. And y equals to negative 1. So we end up with this ordered pair, 0, comma, negative 1. As our first ordered pair that we graph. Okay? When t equals to 1, then again, we have to first of all crack the code for the x coordinate. It's something squared minus 3 times something. And the y is equal to something minus 1. And that something is our parameter value of 1, 1, 1. And so we end up with 1 minus 3. So x is going to be equal to negative 2. X equals negative 2. 1 minus 3. And y equals to 0. So we end up with the ordered pair, negative 2, comma 0. Good. We can also let t be equal to a negative value, about negative 1. So then x equals blank squared minus 3 times blank, and y equals to blank minus 1. And then we let this be negative 1, negative 1, negative 1. So that becomes positive 1 plus 3. So x equals to 4. And over here we end up with y equals negative 2. So now we have the ordered pair 4 comma negative 2. Okay, so far we have 3 points, and when we don't know anything else, we just keep going. Find more values of t. So I'm going to continue in the same spirit. I'm just going to use technology to continue to create this table and then graph these ordered pairs. So I'll just use Desmos for that purpose. Okay, so let's create some tables. And t, and then the first one was t to the second power, 2 to the second power minus t, minus 3t, minus 3t, and the next one was t minus 1, like this. Okay, I want to graph these guys. I want to graph this. Okay, so for example, when we had a 0, we had a 0 and a negative 1. Yep. When t was 0, we had a 0 and a negative 1. And when t was negative 1, we got a 4 for the x coordinate, and we had a y. Okay, so these are my x and my y's. Good. And then lastly, when we had a 1 here, 1, we had negative 2 for x and 0 for y. Okay, so then this is helping me figure out all my x coordinates and my y coordinates. Now, I wish I knew how to graph these two as ordered pairs on Desmos, but I don't, so I'm going to have to do an ugly little trick here of just coming back over here and just putting these as my x and my y and just kind of manually typing them in. 0 there, negative 1 there. And now it should graph that point. So 0, comma, negative 1 becomes this point right there. There, I have 1 point on my grid, right? Okay, not good enough. I got to keep going. Okay, another point on my grid would be 4, and then a negative 2 here. Good. Okay, now I have 2 points on my grid. What about negative 2, and a 0? Okay, so now I have 3 points on my grid. Got to keep going. Okay, so let's keep going over here. How about 2, 3, 4? Okay. Alright, so then this is 0, comma 2 is another point on my grid. 4, comma 3 is another point on my grid. Good. So I'm starting to see a bit of a pattern, maybe. Let's try a couple more. How about some decimal values? How about 0.5? 0.5 will lead to negative 1.25 for my x-coordinate and negative 0.5 for my y-coordinate. So that leads me to another point there. How about if I do 1.5? 1.5 will lead to negative 2.25, and then the output would be positive 0.5. Okay, I'm starting to get a better sense of where this is heading. How about 2.5? How about 2.5? How about 3.5? How about 4.25? Okay, so this is going to be negative 1.25 is mapping with 1.5. That gives me another point there. Positive 1.75 maps to 2.5, and also 5.3125 leads to 3.25. Okay, there. So by hand, pretty painful, but we've started finding these values, right? And it's starting to look like a parabola on its side, maybe, right? And of course, if I wanted to do it by hand, keep going, I can find some more points, and eventually, I would, I think, convince myself that this thing is going to start looking like a parabola on its side. Good. But also, not only do we get a shape, but notice that we get a direction as well, right? As we graph these, this one was the result of, how did we get this as the result? We got this one from negative 1. Good. And then this one was the result of 0, negative 1, 0, negative, that's this one. Right. These should have been in the other order, but okay. And then this one was the result of 0.5, right? So if I ordered these in order, the smallest one is negative 1. I tried it for negative 1. Negative 1, then 0, then 0.5, then 1.5, then 2, then 2.5. And you notice that as t increases, we're going to get this value, then this value, then this value, then this value, then this value. So there's actually a direction that has to happen. This one was the result of using negative 1. This one was the result of using 0. Somewhere in the middle will be the result of using negative 0.5. Let's confirm that. If we go back over here and we type in negative 0.5, we get these ordered pairs. And now if I graph those ordered pairs, I get 1.75 and negative 1.5, and then we get this guy. Okay, so as t increases, here's 0. As t increases 0, 1, 2, 3, 4, 5, right, to infinity, it's going to create this part of the parabola. And then as 0 goes down toward negative infinity, it'll create this part of the parabola over here. Any questions about that? Maybe, sort of, kind of. Maybe, sort of, kind of. Okay, so here's a better picture of the whole thing. We create a table with t values, resulting x values, resulting y values, and as we graph them, we'll end up getting all these ordered pairs that will eventually fill up so many that it ends up looking like a nice, pretty, solid curvature, but it's not, right? It's an infinite number of little dots that are all associated with these. And also you see that there ends up being a direction as well. Negative 2, negative t equals to negative 2, t equals to negative 1, t equals to 0, t equals to 1, 2, 3, right? And then all the little decimal values in between. So when we use parametric equations, not only do we get a shape, a curvature, but we also get a direction along that curvature. Right? We get a third, we get more information. Good? Good, good. Questions, 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 questions? So as t increases, a particle whose position is given by the parametric equation moves along the curve in the direction of the arrows. right? So the little direction of the arrows is important. It's an important element of parametric equations. If we replace t by negative t in example 1, we obtain the parametric equations here and here, right? What were the original ones? The original ones were x equals to t squared minus 3t and y equals to t minus 1. So if we replace each one of these by a negative t, negative t, negative t, negative t, get x equals to negative t squared, well that's just going to be t squared, minus 3 times negative t, that's going to turn it into plus 3t. And then over here we end up with negative t minus 1. So the graph of these parametric equations, okay, so now if we graph these guys, we end up with, the graph of these parametric equations is figure 2, so that's this one over here, and you get the same curve, but traced out in the opposite direction. Good. So replacing t by negative t is going to give you the exact same picture, except that here it traces in this direction, right? It goes this way, and then that way, and then that way, as t increases from negative infinity to positive infinity. Whereas this new set of parametric equations, all it does is change the direction along that same curvature. Good. Questions, 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 questions? Okay, on the other hand, if we replace t by 2t in example 1, we obtain the parametric equations here and here. Right? So again, that equation is just found by looking at y equals to t squared minus 3t and replacing each one of these by 2t. So we get 2t squared minus 3 times 2t, and that's how we get this equation here. And then the other one was y equals to t minus 1. So if we replace the t with 2t, 2t minus 1, we get that. And so that's how we get that equation. Okay, and notice that, in fact, we get, again, the exact same shape. The picture, the graph hasn't changed. But what happens is we trace through it faster. So we just go through it in a faster way. The graph of these parametric equations is, again, the same, but traced out twice as fast. So that's what happens when you replace it by twice t. And if we replaced it by 3t, then it would trace it out 3 times as fast. Good. So thus a parametrization contains more information than just the shape of the curve. It also indicates how the curve is being traced out, the direction and the speed in which the curvature is being traced out. Good. Okay, manipulating these guys. So we could eliminate the parameter and put it back into our standard Cartesian coordinate system. And there's different ways to do that. The most common way is to just do the substitution method. So eliminate the parameter in the parametric equations of example 1 by the substitution method. Okay, so example 1. So if we had x equals to t squared minus 3t, and then we had y equals to t minus 1. Well, pretty easy. What we could do is just take y minus 1, make y plus 1 equals to t by adding 1 plus 1 plus 1 to both sides. Come on. And now we can take this t and plug it right into there. Right, so then this becomes x minus blank squared minus 3 times blank, and we're going to take this t value and dump it in there and dump it in there. So now t becomes y plus 1, and here we get y plus 1. Good. We can simplify it a little bit. X equals to y squared plus 2y plus 1 minus 3y minus 3. And so x equals to y squared minus y minus 2. Okay? Y squared minus y minus 2. Good. And so this is a parabola on its side, which is what we expected. Good. Questions, questions, questions? Yeah. We could do more with this if we wanted to figure out all the information we wanted to. For this guy, we can complete the square, right? And rewrite this as minus y, and then half of this squared, right? So this number right here, minus 1, it's minus 1 times 1/2 squared is the perfect thing to add and subtract. That's going to be minus 1/2 squared, which is equal to positive 1/4. So we'd want to add 1/4, subtract 1/4, right? Minus 2. Then that guarantees the first 3 terms are perfect square trinomials. And so this is going to be equal to y minus 1/2 squared. And then we have this minus 1/4 and minus 2. So as a mixed number is minus 2 1/4 as a mixed number. But then we don't want to leave mixed. This is a mixed. So then x equals to y minus 1/2 squared minus 9/4. Okay, so now that we got it into this form, we can see it's a parabola. You can see the vertex. Right? It's got a vertex at 1/2 comma negative 9/4. But we have to be careful that this thing has been switched, right? Because normally, right, in the normal input-output relationship, we would have it the other way around. Y equals to x minus 1/2 squared minus 9/4. So it's kind of similar, but we're just changing the axes, right? So the vertex of this one is 1/2 comma negative 9/4. So we have to reconsider how that adjusts to this thing. Good. Let's see what the author did. Replaced +1, -1, +2. Oh. Example 1 has a rectangular equation of minus y minus 2, so it's a parabola. Okay, author just stopped there. Minus y minus 2. Minus y minus 2. Good. Okay, any questions? No? No? Okay, so sometimes you'll be asked to find the parametric equation. So find the parametric equations for the line with slope, for the line of slope 3 that passes through the point 2 comma 6. Okay, so it's got a line, it's got a slope. So roughly speaking, we can do a rough little sketch. There's a point at 2 comma 6, I don't know, somewhere around there. And there's a line that goes through it that has a slope of 3. So let's make it in blue. I don't know, maybe something like that. So find the parametric equations for the line of slope equals to 3 that passes through this point. Okay, so remember that every dot on here is an ordered pair, right? And in rectangular coordinates, it would be x comma y points. Right? And one of those points is the point 2 comma 6, since that's that point right there. So we need to come up with an equation for the x and an equation for the y that maintains this relationship. And that relationship is determined by the slope. the slope is this guy. 1 unit here, 3 units there. So whenever the x is changed by 1 unit, the y is changed by a multiple of 3 units. Right? So in general, if this thing is changed by t units, then this thing would be changed by 3t units. Whatever this value is, we triple it, and that's what we get there. Good. However, we have a starting point of 2, so from here I can conclude that the x equation has to be 2 plus t, and the y one would be equal to 6 plus 3t. Good. Let's check and see the first point. The first point at 0, at t equals to 0, we would just get 2 comma 6. Good. Let's find one more point. If the slope is 3, then this point over here should be 3 comma 9. Right? We go out 1 unit this way, 3 units that way, so the 2 changes to a 3, and the 6 goes up by 3, goes up to a 9. So now if this is a 1, if t equals to 1, we get a 3. If t equals to 1, we get a 9. Yeah, that seems to match. Good. So here is our parametric equation of the line that has slope of 3 and goes through the point 2 comma 6. Any questions? Questions? Nope, that's what the author did as well. 2 plus t, y equals to 6 plus 3t. And we can check it by doing our substitution thing one more time. Check. X equals to 2 plus t, and then y equals to 6 plus 3t. Well, the easiest thing to do is to solve for t here. So x minus 2 equals to t. And now that's what we're going to come over here and plug in. Y equals to 6 plus 3 times something. And here is we're going to stick in our t value. That t value is x minus 2. So we end up with y equals to 6 plus 3x minus 6. The 6's cancel, and we get y equals to 3x. And that is a linear equation that has a slope of 3. Right, linear. The original statement said find the equation of the line, so we were expecting the linear equation with a slope of 3, and then just confirm that it also goes to the point 2 comma 6. So if x equals to 2, get y equals to 3 times 2, which is 6. So it goes to the point 2 comma 6. So yeah, it gives us the equation of the line. Got it? Got it? So in rectangular, I could say y equals to, here's a nice little graph for it. So in rectangular, I could say y equals to 3x, right? And that's going to give me that red one, that red line. In parametric, in parametric form, I would have 2 plus t and comma, oh, that looks ugly. Two plus t, comma, 6 plus 3t. It'll still give me the exact same graph, except it'll give me even more information. Right? This guy, the way it's written, also indicates that we have a direction. Starting at this point, it goes that way. When t equals to 0, it starts to head that way for larger and larger values of t. And so therefore, we have a direction that goes like this. As we saw right above, we can also manipulate these equations to change the direction. If I wanted to make it go in the opposite direction, then I would just have to change all the t's to negative t's. If I want to trace through it faster, I can multiply a constant times the t value. Any questions? Okay, and then graphing, like I said, these are really hard to do by hand, so right away we really want to depend on some of our technology to graph some of these things. So let's graph one of them in Desmos first, and then we'll use our calculators to graph these. So use a graphing device to draw the following parametric curves, discuss their similarities and differences between the two. Okay, so let's look at well, actually, I don't know. Yeah, let's just go to our calculator. Okay, the first thing we want to do when we get to our calculator is go over to where it says mode. And now we had polar, right? We normally work with functions. We just work with polar, and now we want to go here where it says parametric. So go down, down, to the right, down, to the right. Parametric, hit enter, and now the calculator knows we're in parametric form. Okay, all right, so now if we go over to y equals, now it'll give you an x sub 1 and y sub 1 t for each little grouping. Now it knows you're in polar. You need an equation for the x-coordinate, an equation for the y-coordinate separate, right? And they're both going to be functions of t. So the x-coordinate, let's type in sine 2t, right? And that same button that used to have an x, and then later when we did polar, did a theta, now it does a t. Right? The calculator knows that you're in parametric form. Good. So now we want to do 2 times cosine of t, like this. Good. Next, let's go to our window, and now we have to give a range for the t values. Good. Now, t values happen to also be angles in this, right? Because we have cosine of something. Cosine of something. So the domain, the thing you plug into a sine function, is an angle. So 0 to 2 pi seems appropriate. An appropriate place to start and see what happens. Good. Now, for the x and y, that's going to be a little trickier. Okay, so the x-coordinate is going to be bounded between -1 and 1, right? The sine function is bounded. The y-coordinate is going to be bounded between -2 and +2. So let's just pick some values. This should be fine for the x. And let's make it -3 to +3 for the y, just to make sure we capture everything. We can always come back and guess and check different things. So graph it, and we get that. Good. Like an hourglass symbol. Any questions, any questions, any questions? No? 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 Okay, they also give us another pair over here. Let's go back over here. Now, I don't want to erase these right now, so let me just highlight the equal sign, hit enter, and then it'll unhighlight them. See how they used to be dark? That means that the calculator will continue to save those equations, but it's not going to graph them. Okay, so now if I try the other one, sine of 3t, and then 2 cosine of t, 2 cosine of t, close. Now let's graph that one. Okay, we're going to leave it for the same window, and we get that. Good. Questions, 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 questions? How to graph it? Okay, so in both parts A and B, the graph will lie inside the rectangular, rectangle given by -1 to 1, right? That's because the sine is bounded by -1 to 1. This 2 or this 3 change how frequently we complete a period, so it'll oscillate faster through its period, but it doesn't change the amplitude of the sine function. It's still trapped between -1 and 1. And this 2 right here changes the amplitude, so it's bounded between -2 to +2 for the y coordinates. Good, good, good. Since both our sine and cosine numbers lie between -1, okay. So we tried that rectangle. Okay, so there you go. You just have to use your technology to graph it. That's all these questions are going to ask you to do. Right? So we know that each one of these little points on here is an input-output, an x comma y, where the x is actually this equation and the y is the result of this equation. Both of them being manipulated by a third variable that's not in my grid here. It's the t variable, right? The t parameter. And the t parameter, in this case, is ranging from 0 to 2 pi. Good. And then we got this one for the other equation. Good, good. Both graphs are closed curves, which means that they form loops within the same starting point and ending point. Also, both graphs cross over themselves. Right? So these are similarities between the two. However, the graph in 12a has 2 loops like figure 8, whereas the graph in 12b has 3 loops. Okay, well, there you go. The first graph and example are called, I don't know how to pronounce that. Lissajous figures. And the graph of a pair of parametric equations of this form. So anything that fits this form will give you that same sort of figure. This fact can be used to choose a viewing rectangle. Okay, so just playing around with your calculator, find different results. We can also combine the two ideas. We can have a parametric equation and then also graph it in polar. So polar equations in parametric. So the parametric just refers to the idea that the x-coordinate and the y-coordinate, the input and the output coordinates, are themselves equations of a third variable. So now in polar, we'd have the input angle and the output r value themselves are equations are of a third variable. Good. So the graph of a polar equation r equals to f of theta is the same as the graph of the parametric equation x equals to f of t cosine of t and y equals to f of t sine of t. So that's the conversion factor we're going to use. And so just use this example. Express the equations in parametric form. So the given polar equation is equivalent to the parametric equations. Oh, r equals to theta is the equation. Consider the polar equation r equals to theta. So we'll express the equation in parametric form. So part A, x equals to t cosine of theta, and y equals to t sine of theta. And then we can graph them. So it ends up being a spiral. It looks like this. So just use technology to graph them.